Break, we have one additional speaker, Professor Yuri Pershin from University of South Carolina. He has his doctoral degree from Germany and has been a postdoc researcher at University of California, San Diego, where he worked closely with Professor Max DeVentura. You probably may remember him. He gave a presentation in 2008 in the first symposium, and Leon highlighted some of his work. Professor Pershin's research interest is as a physicist in computational theoretical nanophysics, including Memristors. So, thank you.
Thank you for the introduction. Okay, first of all, I would like to thank organizer for giving me this opportunity to represent our recent and ongoing work. And I'm going to talk about generalization of the concept of memory resistance to other circuit elements, to capacitors and inductors. So this work was done mostly in collaboration with Max DeVentura from UCSD, Julian Martinez and Matt Krams, the radio students. And we also collaborated with Leon Chua on the definition of Mem-capacitors and Mem-inductor systems and their properties. This is a brief outline of my presentation. So I will focus, in the first part of my presentation, I will focus on Mem-capacitive systems. I will consider the definition of the system, general properties, and give few examples of this system. In the second part of my talk, I will talk about circuits with memristors. So we have developed a simple circuit which can emulate any kind of memristors, and demonstrated the possibility of different, more complex circuits with memristors, including circuit which can emulate Mem-capacitors and Mem-inductors. So this is a definition of Mem-capacitor system. So the main idea is to consider the capacitors which can be a function of internal state variables, which denoted by x, charge, and time. And we also supplement this first equation by a dynamical equation for the state, for dynamics of state variables. So this is an example of charge-controlled Mem-capacitive system. This is equations for the voltage-controlled Mem-capacitive system. And in general, the definitions are very similar to the definition of memory resistive system given by Steve Kang and Leon Chua in their 76 paper. So these definitions are very general, so they can include a lot of different elements and their combinations. There are just a few examples of those elements. So one of them is perfect voltage-controlled Mem-capacitors, and in perfect Mem-capacitors, capacitance is just a function of the integral of voltage applied to this capacitor in time. Another possible elements that are covered by this definition are so-called alpha and beta capacitors that were defined by Leon Chua in his 2003 papers. We also found that systems with nonlinear resistors and capacitors, they also can fall into this definition. And possibly there are some other elements which can be described by this type of equations. Concerning general properties of this system, we can mention their typical low frequency behavior. So low frequencies memory capacitor should behave like non-linear capacitors. At high frequency, they should behave just like linear capacitors. For well-defined capacitance, like for non-infinite and non-zero capacitance, QVC curve should be a pinched hysteresis loop, so it just simply follows from Q equal to C times V. And the most interesting properties of Mem-capacitors is a possibility of energy storage. So capacitors, they of course can be charged and they can store electron, but also for Mem-capacitors it's very important that they have some internal system, and this internal system can store energy even in the fully discharged state. So if we don't have any electron charge, we still can have some energy previously taken from the electron system stored in the Mem-capacitor. To understand this feature, I can consider just a pinched hysteresis loop of a memory capacitive system. So I plotted in charge versus voltage coordinates, and the meaning of the hysteresis loop for Mem-capacitive system is more general, and because then the meaning of the hysteresis loop for Memristor system, because this area which is shaded here, this area they give us just energy stored in Mem-capacitor. So the sign of this energy that is stored is depends on the way in which we go along the hysteresis curve. So if we go this way, this energy U2 will be positive and the energy U1 will be negative, and that means that in a first half period when the applied voltage is positive, we just add some energy into the Mem-capacitive system. So I start from here and end here. We end this energy which is given by the area of this inside of the loop, and during the negative half period we remove the energy Q1 from the Mem-capacitive system. Therefore we can have three different cases. So if the sum of these energies Q1 plus Q2 is equal to 0, we have a non-dissipative Mem-capacitive system. So we take the same amount of energy that was previously added. If U1 plus Q2 is greater than 0, we have dissipative Mem-capacitive system. And if U1 plus Q2 is less than 0, we obtain an active Mem-capacitive system. So these equations that were introduced previously, they allow all these possible situations. However, if we start from a physical model of Mem-capacitive device, we mainly should obtain non-dissipative or dissipative behavior, because certainly capacitors, they are not active devices. Concerning physical mechanism of Mem-capacitance, so we can just consider usual expression for parallel plate capacitor. There are three parameters here. So actually we can play by any of these parameters and obtain memory capacitive behavior. So one possibility is to have a time-dependent permittivity epsilon, and it can be realized in two different ways. So we can construct, for example, a system with very low polarization or depolarization times, and I'm going to talk in more details about such a system. And similar systems, they were actually realized experimentally, and they are based on nanodots embedded into capacitors. Another way is to switch permittivity between two states, and I believe that it was realized by Hewlett-Packard group. And second parameter is the area of plate, and it's difficult to play with this parameter. And the last parameter is separation between the plates. So separation between the plate can be varied in Mem-capacitors. So it's Mem stands for microelectromechanical systems. And also we can have a variation between the plate in an ionic system when we have a filament which grows between two electrodes. So effectively we change the separation between filament. So in this system, Mem-capacitive and Memristor effects, they can appear simultaneously. Okay, I'm going to show several examples of non-capacitive systems. So this is just a toy model. We have a parallel plate capacitor with a fixed bottom plate and top plate suspended by spring. When I put some charge on the bottom plate, then these plates they attract to each other and separation between plate changes. So we obtain some kind of memory in the which is encoded in the distance between the plates. So here is the expression for capacitance and parameter y, which give us displacement from the non-charged position of the top plate. It changes. So it changes accordingly to the second order differential equation. We can also put here some dissipation, parameter gamma, and this term describes just attraction between the plates. So it's clear that these equations they fall into the category of second order charge control Mem-capacitive system. So if I do a simulation of this system, I obtain actually this kind of hysteresis loop. So for charge versus voltage, our loops I have a pinched hysteresis loop. At high frequencies, system behave like a linear capacitor, and at low frequencies, the system is almost like behave like a nonlinear capacitor. And actually, if I apply a voltage pulse to the system, and after that voltage is zero, so I remove all the charge, there are oscillations which are retained in the system, and this oscillation actually keep a memory about the past. However, this previous system is certainly not very useful because relaxation time is pretty short, and this is another example of Mem-capacitive system. Is based on a flexible membrane, so it's another way to dispose transparency. So if I take Mem-capacitors, so one plate is just fixed plate, and second plate is a strained membrane, and then there are two equilibrium positions which can be actually realized, so it can be folded up or down, so I just squeeze the membrane. And in the down state, the capacitance is high because membrane and plate they are close to each other. In the upper position, non-capacitance is lower, and applying voltage pulses, I can actually switch the membrane from up to down state and vice versa. To model the system, we use just double well potential, and this is the result of simulation. So at certain parameter, we again obtain a typical behavior of a capacitive system. So what is interesting here is the attraction between the plate does not depend on the polarity of the voltage. So in any case, plates will be attracted to each other. So in order to switch to the high to the low capacitance plate, we propose to put more charge on the plate, and after that we can just release, and elastic energy conserved in the system can make the membrane move up. So we pull it down, strong, release, and so we can switch between top and bottom state. However, this is not the most interesting feature. So let me consider a simple circuit of consisting of this membrane and capacitive system and power source, and let me apply several periods of AC voltage. Next, what I'm going to do, I'm going to plot the capacitance, measure it at a certain moment of time. Here it's at 40 T0, and I'm going to vary the voltage amplitude. So this is a result of simulation. So for low and high voltage amplitudes, I obtain just very smooth lines. However, there is a certain limit in which the behavior of the system is chaotic. So I change voltage just a little bit by small step. However, the result, the capacitive at the final moment of time changes significantly. And even if I scale, for example, here, and then I obtain again chaotic behavior. So this is a very interesting example of chaotic behavior in electronics, which is possible in a system with only one single element. And the last example of Mem-capacitive system is based on a slow polarizability of a medium. So here you can see the parallel plate capacitors with a set of metal layers inside, and when we put a charge on the external plate, then electrons start to tunnel between the plate, and the tunneling time is pretty slow. Therefore, we can polarize at a certain applied voltage this internal medium, and later when we change the voltage, this polarization will stay for a certain amount of time, and in this way we obtain a memory. And here you can see some results of the simulation. What is interesting is that in the system, the QV plot is not a pinched hysteresis loop, and in the dependence of capacitor on the voltage, we can observe that capacitance can be zero, and it can also be infinite. This comes from overscreening of this medium of the internally applied voltage. Another interesting feature of this model is that it can be realized by usual circuit elements. So the equivalent model just of two-layer system consists of three usual capacitors and a nonlinear resistor which shunts the middle capacitor. And this is the second part of my talk. It's about emulation of memory devices. So here the motivation is that currently it's single memristors, they are not available. It's very difficult to make them. However, there is a need of them for educational purposes and also for proof of concept of circuits with memristors. And in order to solve this problem, we have realized the following memristor emulator. So the main element in this emulator is a digital potentiometer here, and the wiper of the potentiometer and one of the electrodes, they serve like external connection of Mem-capacitor. And also this circuit contains analog to digital converter, which allows to read the voltage applied to the Mem-capacitor, and microcontroller, which actually contains a program, and this program calculates the value of resistance of digital potentiometer accordingly to a pre-programmed equation. So we can write any program, we can program any equation, therefore we can obtain almost any possible Mem-capacitive system. And this is a real picture of the device. So this is a hysteresis loop that we have obtained for certain value of parameters. And we used the memristor emulator to build several circuits with memristors. So this slide shows application of memristor in analog circuits. So here the main idea is to use memristor at low applied voltages in the analog mode of operation and use a high voltage amplitude in order to change the state of memristor. So we know that many memristors, they have a threshold type of behavior. Therefore, when we apply low voltages, the value of memristor stay unchanged, and it can be safely operate as an analog element. So this example shows a programmable gain amplifier. So when memristor, and we use memristor emulator instead of memristor, but in the future, of course, we can use real memristors in these circuits. So the ratio of R1 to M defines the circuit gain, and this pictures actually show that applying a train of pulses, we can change the gain of amplifier. So we apply here on the positive input a constant voltage, and here we monitor the output voltage. So output voltage changes at each pulse, and changes actually because the state of memristor changes. So we can actually change the pulse width and obtain more rough change of the gain. Another circuit that we have realized is a small neural network. So in this network we used 3 neurons and 2 memristors as synapses. So the neurons then were realized also using some small electronic circuits, and the basic idea is that depending on the input on them, they can or cannot send a train of pulses, so both in forward and back direction. And it follows from our simulations and from the main idea is when we have a correlation between first and second input, or between sight of foot and sound, then the state of the second memristor can change or changes, and therefore this simple neural network demonstrates the learning. And here we realized emulators of Mem-capacitive and Mem-inductive system based on Memristors. So the main idea is to use a modified generator scheme. So generator is a scheme which is used to replace large value inductances in electronic scheme. And there are, in order to explain the behavior, we have 2 current passes. One is like this, and second one is in this direction. So here A1 is operational amplifier. And this path is like a console path, so just a very low current flow through it. And operation amplifier operates in such a way that we can think that here voltages at positive and negative inputs are the same. So from that it follows that this system can be approximately described by this equivalent circuit, where the time dependence of memristor resistance is mapped on the time dependence of effective capacitance. And replacing the places of capacitor and memristor, we can actually obtain equivalent Mem-inductive behavior. And this simulation actually shows that the value of capacitance and the value of inductance in the circuit changes. And here are my conclusions. So we introduce Mem-capacitive and Mem-inductive system, which are generalizations, independent generalizations of usual capacitors and inductors. Physical models of Mem-capacitors show interesting features, such as Antwick hysteresis loops and chaotic behavior. So it's interesting that we can obtain chaos in a circuit with only one circuit element. And we also demonstrated Memristor emulator. Memristor emulator can emulate a very wide range of memristive systems, so we can emulate even perfect memristors. So only those memristors which are not possible to create experimentally up to now. And there's important application of emulator in education, so we can teach a new generation of engineers to memoristic, Mem-capacitive, and Mem-inductive technologies using this emulator. Thank you for your attention.
Thank you. Is there any question? We can entertain one question. Yes, Stan, please.
So with your chaotic behavior that you saw, do you have a way of testing to determine that that's truly chaotic behavior, or could it still possibly be essentially high frequency oscillating behavior that is at higher frequency than your simulation was able to carry on?
How to test this? Actually, I made a literature search and I found that previously, theoretically, chaotic behavior and doubtful well potential was discussed. So it's, but how to show that, how to distinguish? Possibly we can just reduce a step, but we already did that. Even with a small change in voltage, we are obtaining this kind of chaotic behavior. My student now calculate Lyapunov of exponents for this here, so probably they can provide also some information, be as additional proof. Yes.
Okay, thank you very much for your wonderful presentation.